We're talking about the nature of the CX bond. Here you can see the electronegative element is present here. So it is having delta minus and carbon is delta plus. Because you can see there is a charge separation. As a charge separation, we mentioned the carbon halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge, whereas the halogen atom bears a partial negative charge. As I am going down the group, what happens? Fluorine to iodine. As I am going down the group, we know very well the size increases. That means we are discussing between CF and CI. As I'm going like this, fluorine is small, iodine is too big. Fluorine atom is the smallest and iodine atom is the largest. Consequently, what should have happened? Fluorine is very small here, so definitely it will not just push the carbon very away. So it has to keep it intact, very close together. But here, iodine is too large, too large. So therefore, the inter-electronic attraction between the carbon and iodine will be less. Why we are discussing this? We are discussing about the nature of the CX bond here. When I am comparing between carbon and fluorine and carbon and iodine, fluorine is small. So the inter-electronic interaction between them is very strong. But when you are discussing between carbon and iodine, the inter-electronic attraction is very less because of their size. If the attraction is very less, definitely they can be distant away. Therefore, I can understand it. Bond length should be more. Here the bond length will be less. Consequently, the carbon halogen bond length increases from CF to CI. We can understand it by this way. There is also another phenomena by which we can understand. Consider I am having CF and CI. Fluorine is very electronegative. Iodine is not that much electronegative. So what will this fluorine do? Keep pulling the electron towards itself. But iodine is not like that. If the electron cloud is much pulled by fluorine, definitely carbon has to be very close to fluorine. But here it can be a distant away. We are discussing the increase in the bond length of carbon halogen in two aspects. One in atomic size aspect, another with respect to electronegativity. The tabular column is showing you the bond length, bond enthalpy, and dipole moment order. With all the methyl halides are provided to us, what do you observe? As you just said that fluorine is smaller, iodine is too larger, you can see as I am going down, the bond length has increased. Let us look at the bond enthalpy here. What do you mean by bond enthalpy? The amount of energy that you should supply to break the bond between them. We just now mentioned carbon and fluorine is very close with each other, intact. But carbon and iodine is distant away from each other. So why do you need to spend so much energy in breaking them? Anyhow, their attractive force is less only. Here the attractive force is very high. So here I have to supply massive energy, high energy I should supply to break the bond. Look at this down the group. The bond enthalpy value decreased. Let us go to dipole moment now. What is dipole moment? The symbol mu is given as dipole moment. Its SI unit is called as d by. Dipole moment tells you about this polarity. How polar is a molecule? If I say mu is equal to 0, it is a non-polar molecule. If I say mu is not equal to 0, then it is a polar molecule. You can understand in the very beginning, we said that Rx is creating a charge difference. So definitely they are polar. You can see they are having some net dipole moment value is available. Let us look at the trend here. We can find CH3Cl is having more dipole moment compared to CH3F followed by CH3Br followed by CH3I. Ma'am, you said dipole moment means charge difference. In that case, fluorine is very much electronegative. Chlorine is a little bit electronegative only, no. Then what is our expectation? Our expectation is that CH3F should have higher dipole moment than C3Cl because of the higher charge difference. Electronegativity value difference is too high here. Then why this kind of a trend has been observed? Because dipole moment is given by Q multiplied by bond length, where Q stands for the charge, bond length is the length between them. Okay, pa? Here, since chlorine is a little bit larger than the methyl, than the fluorine is a little bit less, you can see the bond length has gradually increased. Because of the increase in the bond length, the mu value of CH3Cl also increased. Ma'am, but fluorine is having high charge separation. So with that, the compensation should have happened. Here, with respect to CH3Cl and CH3F, instead of Q value, the Bl value governs the dipole moment. Other than that, you can see it is following the same order only. It depends upon the charge separation, charge difference. Clear about this?
Yes, ma'am.
Right. We're going for the preparation of haloalkanes. The very common method of preparing it is using zinc chloride as a catalyst by treating it with some HX, ROH plus H plus goes for protonation, RO plus H2. This gets cleaved, yes, so that the Cl minus can come and attack so that it gets cleaved. So I form RCl plus H2O. Very common method of preparation of an haloalkane by using HCl in the presence of zinc chloride. The other very common methods here is usage of PX3, 3 moles of alcohol in the presence of 3x because there is 3x here, right? So I get 3 moles of RX plus H3PO3, phosphorus acid. Here X can be either chlorine or bromine. Instead of PX3, you can also use PCl₅ here. Here you can see the X is either chlorine or bromine. But here we are very specific. It is PCl₅, phosphorus pentachloride. In this case, what is happening? I get RCl. I get POCl3, phosphonyl chloride, plus HCl. You need to remember the side products of these reactions. When you use PX3, what is your product? If you use PCl₅, what will be your product? The same reaction can also be done in the presence of red phosphorus and a halogen. The halogen could be either bromine or iodine. We don't prefer chlorine here. Instead, we prefer only bromine or iodine. And you can see the OH is getting replaced by X here. Among all these methods, this method is the best method. It's because the compound that you're using here is called as thionyl chloride. Here you can see ROH is getting converted to RCl plus SO2 plus HCl. Both of them are gases here. Since it is the gases, they themselves will leave the container. So it's very easy for me to recover my product. Product recovery is easy for me. So this method is the best chosen method.
Ma'am, what is
Hmm.
red P again?
Phosphorus. There are three types of phosphorus: black phosphorus, white phosphorus, red phosphorus. For this, they use red phosphorus. The next method is I use alcohol in the presence of NaBr and H2SO4, where you get RBr, sodium hydrogen sulfate, and water. The whole method procedure is giving you an idea how do you convert an alcohol into halides. Okay, now let's go on. The hydroxyl group of an alcohol is replaced by halogen on reaction with concentrated halogen acids. Concentrated halogen acids, phosphorus halides, or thionyl chloride. Here, we prefer thionyl chloride because in this reaction, it is formed along with the gases sulfur dioxide and HCl. These two gaseous products are escapable. Hence, the reaction will provide you pure alkyl halide only. But look at this case. I am having water along with it. I am adding sodium hydrogen sulfate. I am having POCl3, POCl, H3PO3, HCl. All of them will be available in the container in the same reaction mixture itself. That means I have to purify this product. I have to extract this product out of it. But here, what I get is purified form already. Nothing is available with it, along with it. The reactions of primary and secondary alcohols with HCl requires the presence of a catalyst, zinc chloride. If I'm having primary alcohol, sorry, or a secondary one, in that case, the zinc chloride is necessary. A catalyst is required. But if you do the same reaction with tertiary alcohol, you don't need a catalyst at all. Just by simply shaking the alcohol with concentrated HCl at room temperature, the reaction is over. Why is that? Consider I am having CH3 triCOH, a tertiary alcohol. To this I am adding HCl. It forms O plus H2, where the water, if it is leaving, it will form the very stable tertiary carbonium ion. Because of the stable tertiary carbonium ion formation, you don't need to boil it at all. Just by shaking, the reaction is over. And the end product will be the chloride attack on this carbonium to form this RCl. And this reaction that you are seeing right now comes as a qualitative analyzer called as Lucas test. The test is called as Lucas test, which is performed for alcohols. Here, tertiary alcohols are super faster compared to secondary alcohol compared to primary alcohol. Constant boiling with HBr 48% is used for the preparing alkyl bromide. Here I use HCl. If you are making it as RBr, use HBr 48% to make alkyl bromide. You can also prepare RI by heating alcohols with sodium or potassium iodide in 95% orthophosphoric acid. So if you want to convert this alcohol into RI, you need to use NaI or Ki in the presence of H3PO4. If you use it, the reaction is over. The order of reactivity of the alcohols with a given halo acid is tertiary greater than secondary greater than primary. That's what we wrote it just now. Phosphorus tribromide and triiodide are usually generated in situ, very important word. PBr3 or Pi3 are generated in situ. Within the reaction mixture itself it is formed. Where is that? Look at this reaction here. I said red phosphorus plus X2. This is will give me Pi3 or PBr3. I don't want to separately take this compound. Ma'am, I'm preparing PBr3 and then I'm adding to the reactant. Not necessary. Take the red phosphorus, add it with halogen where it will form Pi3 and PBr3. Such reactions are called as in situ reaction. That means you are generating your requirement within the reaction mixture. I am not taking the exact compound. Instead, the compound is generated within by certain reactants there, produced in the reaction mixture by the reaction
Ma'am,
of. Mm,
ma'am, so in situ means like there are two different compounds and it could be any of the compounds?
it could be two different compounds. Then what you're saying?
And it could be any of them? Is that what it means?
See, in this reaction, I am taking PBr3. I am not taking PBr3 in the next reaction. Instead, I am taking red phosphorus plus Br2. I don't waste my time in synthesizing this compound and then adding to my alcohol. Instead, I take the precursors, the reactants that will form PBr3.
Oh, okay, ma'am.
Oh, okay, ma'am.
So what am I doing? I'm actually saving my time there.
But will H3PO4 be formed? H3PO3?
H3PO4.
Will
Yeah,
H3PO3 be
that will
formed?
be formed. That will be formed. Yes.
So that phosphorus is basically like a shortcut method.
How did we generate this PX3? This is also from phosphorus only. What is the
Okay,
difference
ma'am.
between
Yeah.
these two processes? Here I am taking the reactant which I wanted. So to prepare this, for example, I am taking half a day. To do this reaction, I am not wasting my half a day. I am taking what is required to prepare this PBr3 and I am putting along with alcohol. So that they too will react to form PBr3 and they will react with alcohol. That's the difference.
Okay, ma'am.
The preparation of alkyl chloride is carried out either by passing dry hydrogen chloride gas through a solution of alcohol or by heating a mixture of alcohol and concentrated aqueous halogen acid. Either you take the alcohol, you treat it with dry HCl gas, or you take the alcohol with concentrated aqueous HCl. Both the things will provide you alkyl chloride. The above methods are not applicable for the preparation of aryl halides. You can't prepare them. Why? Because when I'm talking about phenol and I'm talking about methanol, here you can see this oxygen is bonded with the carbon which is involved in resonance. Here is the OH. So I can understand definitely this lone pair of electron and oxygen should have went for resonance with benzene so that it will be forming a partial double bond between this carbon and oxygen. A partial double bond is formed between the carbon and the oxygen. So here, can you easily replace this by some other nucleophile like chlorine or bromine? It's not possible. But here in this case, I'm having CH3 which is a single bond. Here I'm able to replace this OH by Cl minus. Understood, Ra? The question appears in 2 mark section. Why you cannot synthesize chlorobenzene from phenol just by using HCl because you create a partial double bond character which makes this bond strong. So it's not easy for you to break this bond. But in this case, there is no partial double bond, it's just a single bond here. So it's easy for you to replace the OH by Cl. Okay,
Yes, ma'am. I got it.
we are going for free radical halogenation. Basically, you chlorinated or you brominated. Where you'll be giving mixture of isomeric mono or polyhaloalkanes, which is actually difficult to separate. So this method is not the right method. You generally don't prefer this method to synthesize. alkyl halides from alkanes. How do we do this? We use free radical mechanism. Consider I'm having butane. To this I'm adding chlorine in the presence of UV. This Cl2 in the presence of UV will undergo homolytic cleavage. That means breaking the bond in the middle, so that both of them will be getting free radical. 2Cl dot you form. This step is called as initiation. Now this Cl dot is very active species. It's very active like an LKG UKG kid who cannot sit in one single place. So what it does, it is going to trigger the homolytic cleavage of the butane. It is making the butane to go for a free radical cleavage. Now what do I have? I am having CH2 dot. Cl dot will combine with each other. The official arrow mark says only one electron is there. Each electron is coming for the bond formation. I have formed this product. What you are doing? You are doing free radical monohalogenation. You are doing free radical monohalogenation. Okay, ma'am. Is that over? Not yet over. Then what would happen? Why only this hydrogen should go for participation? Even this hydrogen could have went for participation, no? Having this, what about this broke like this and the Cl dot got connected with this carbon like this. Like this, the reaction can keep going on till it reaches a termination step. So what are the compounds that's possible? It could have got formed here. It could have got formed here, right? Two products are possible. What else could have happened? This H dot and Cl dot could have combined to form HCl. The Cl dot and Cl dot could have combined to form Cl2. This free radical would have combined with its own free radical to form an alkane. All these reactions occurs in termination step. Termination means no more free radicals are available. It's over. So this particular reaction gives you multiple compounds. That's the reason why you say it is not a prominent method in synthesizing haloalkane. Your yield will be very less. The free radical chlorination or bromination of alkanes gives you a mixture of isomeric, mono and polyhaloalkanes, which is difficult to separate as a pure compound. Consequently, the yield of any single compound is low. If I add only one compound, then I say it is 100% yield. But several compounds are there. Obviously, they have got fractionated, right? Too many are there present in the mixture. So therefore, the product of the yield goes down. Understood this method?
Yes, ma'am.
The next method, from alkenes, we are synthesizing it. I take HX, H plus and X minus. The double bond gets attracted to the H plus here at first, right? Okay, da? So that X minus jump for the attack on the carbonium to form this compound. Now this is a symmetrical one. I don't have any difficulty in finding my product. What if I am having unsymmetrical alkene? Use the Markovnikov's rule. The negative part, which is negative, iodide is a negative part, which will get added to the more substituted carbon of the olefin. Which is more substituted carbon? This is the more substituted carbon. So I have two products here. One product is where the iodine goes and attacks the more substituted carbon and the CH2 takes the hydrogen. One product. Another product where the iodine goes and gets attacked here. Two products are possible, but which is the major product? This is your major product. This will be your minor product, because you are following according to Markov, the negative part should get added to the more substituted carbon only. So this is the major product. Clear, Ada?
Yes, ma'am.
We are trying to add. So in this method, you can use HCl, HBr, HI, anything is fine. You can see HF is never coming for the role at all. We generally don't use HF, which is not that much reactive with any processes for us. I am trying to add an halogen in the presence of carbon tetrachloride, a non-polar solvent. The reaction is called as halogenation reaction, dihalogenation reaction. Look at the product here. You can see when I added bromine, the double bond got single bond. You can see two Br are getting added here in the product. This is a qualitative test for unsaturated compounds, where if you are having unsaturation, this bromine would go and react with it to form this product here. Bromine initially we know it is a reddish brown color liquid. Okay, so once it is getting added here, it loses its color. So if it is a compound which is having double bond or triple bond, when it reacts with bromine, it will become the final solution will be colorless. With that, you will be able to understand whether it had unsaturation or not. In the laboratory, addition of bromine in CCl₄ to an alkene resulting in discharge of reddish brown color of bromine constitutes an important method for the detection of double bonds in a molecule. What is this discharge? That means disappearance. No longer it is available. It went out. The addition results in the synthesis of vicinal dibromide. What is vicinal dibromide? The bromine is present in the vicinity. In the neighboring carbons, adjacent carbons is having bromine. Initially it was reddish brown, now it has become colorless. Clear that?
Yes, ma'am.
So identify all the possible monochlorostructural isomers expected to be formed on a free radical monochlorination of this compound. CH3 twice, correct? This is CH3 twice, CH2, CH3. Monochlorine means only one chlorine can get added here. So let's start. I can add the chlorine here. 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 Because both are at the same carbon only. If I bond chlorine here or if I bond the chlorine here, both are same only. So only I will take one thing as into consideration. You understand? In order to avoid your mistakes, please write the IUPAC nomenclature of them so that you don't repeat the compounds or you don't miss the compounds. Okay, ma? Shall we continue?
Yes, ma'am.
The next reaction is halogen exchange. The reaction is called as Finkelstein's reaction. Halogen exchange itself, we can understand there was already an halogen. With this, an halogen is getting exchanged here. That's your meaning. Finkelstein reaction is helpful in converting an alkyl halide into iodoalkane. They'll be giving you in 1 mark section. Write the following reaction. They'll just say Finkelstein, Swarts, etc. You should know what is Finkelstein. You just need to write this reaction, nothing else. You need not describe it and all. Write the reaction. For this, what is your reagent? Sodium iodide in dry acetone. Acetone is your solvent here. Sodium iodide in dry acetone. So NaI will get split up as Na plus and I minus. I am having Rx. I minus will attack this R and the X minus will leave out. So that I get Ri. So this Rx could be either chlorine or bromine, no problem. NaCl or NaBr, I am forming in side product here, thus formed, is precipitated in dry acetone. Very important. You could have used anything. Why dry acetone specifically? And I'm going to treat this in the presence of dry acetone. They are getting precipitated in the dry acetone. So what? Let it get precipitated so that this product will no longer be available. From chemical equilibrium chapter, we should have studied Le-Chatelier's principle. If this one that is present in the product side is getting consumed instantaneously, definitely what will the reactant do? The reactant tries to push the reaction forward so that it forms still more NaCl and NaBr. My expectation is not NaCl and NaBr. That is not my prime product. My product is Ri. I want this only. But in order by removing this side product, the reaction is made to move forward so that I enjoy my expected product here. Clear?
Yes, ma'am.
The synthesis of alkyl chloride is best accompanied by heating an alkyl chloride or bromide in the presence of metallic fluorides. So we synthesize iodide, that was called as Finkelstein. If I am going to convert an RX into RF, then that reaction is called Swarts reaction. Here, basically, we use any salts of fluorine, AgF, Hg2F2, COF2, SbF3. These things we must definitely remember. They will provide you an MCQ asking you to find out which one of them will provide you Swarts reaction. So we need to remember what are the salts that will provide the Swarts reaction here. Okay. We are moving for the preparation of haloarene. So till now we have converted an alcohol into alkyl halide. We took an alkyl halide and we wanted to convert it into our desired alkyl halide. Two reactions are over. Now we are taking haloarenes. What are haloarenes? Benzene to which halogen is added. I call it as haloarenes. We know benzene usually undergoes only electrophilic aromatic substitution reactions. You can see from hydrocarbons by electrophilic substitution. The first reaction is Friedel-Crafts halogenation reaction. Friedel-Crafts halogenation reaction. The compound is called as toluene. We are treating it in the presence of X2 in Fe and dark. This is how you generally do this reaction. This dark condition is very important for us. People also use FeBr3 or FeX3. Either they just take raw iron or they add iron halide to it. What happens here? X2 in the presence of FeX3. This is a Lewis acid. I am having X2 here in the presence of FeX3. This will take X minus so that what is remaining? X plus FeX4 minus is formed. X plus and FeX4 minus form. This is an electrophile. Now this electrophile will go and attack the benzene to form your product. Same logic is happening here. Toluene, the presence of X2 and Fe is going to form halogen substituted toluene. We know methyl is an activator, it's an ortho-para director. So it directs this halogen to either ortho position or to its para position. So I have ortho-halotoluene or para-halotoluene. Okay. So you can easily perform this reaction to synthesize aryl chlorides and bromides. You will be able to separate these isomers due to their large difference in their melting points. Their melting point difference is too high here, so therefore I can easily separate them. Reactions with iodine are reversible in nature, very important, and requires the presence of an oxidizing agent, HNO3 or periodic acid, to oxidize the HI formed during iodination. I am having benzene is there, I want to iodinate it. So if I am using I2 in the presence of Fe, this will form iodobenzene along with HI will be formed. This HI has to get, what should I do? This is always a reversible reaction because of the bulkiness of the iodine. The reaction is reversible because of the bulkiness of the iodine. So what do? I require an strong oxidizing agent so that the HI that has got generated can be further oxidized. HI here is present in -1 state. So using the strong oxidizing agent, you can further oxidize it to iodine itself, which is a gas, right? You can remove it. Fluoro compounds are not prepared by this method due to the high reactivity of the fluorine. You can't do fluorine here. If you do iodine, use stronger acids to convert the HI to iodine. Okay.